Okay, yeah, we're going to talk about electronic measurements for amateur radio. I'm Bob Witte, K0NR. I'm in Hartselle, Colorado, kind of right off Trout Creek Pass. And I'm happy to be here tonight. My technical background is electrical engineering, and I worked for over 4 decades in electronic test and measurement. And my ham radio interest these days has been kind of VHF, mountains, exploring, SOTA and POTA, and then I do a fair amount of writing. During my career, I wrote 2 books on electronic measurements, so it's something I enjoy talking about. I wasn't quite sure where to target this, so I ended up kind of going down the middle of the road, not too basic, but not too advanced either. If you have questions where you want to drag me to a more basic discussion, that's fine. Or if you have more advanced questions, we can deal with that too. And what I thought we'd do is do a little bit of introduction, but then first thing I want to hit is two basic pieces of test gear. I think everybody should have every ham should have is a digital multimeter and an SWR meter. And then we'll take a look at oscilloscopes, VNAs, and spectrum analyzers. So why do we need electronic measurements? Well, here's my first law of electronic measurement. With electricity, most of the time we cannot observe what is going on without measuring instruments. We need help seeing what the circuit is doing and quantifying its behavior. So that's why we need measuring instruments. And then the second law is, on those times when we can't observe electricity directly, it's often a really bad thing. Sparks are flying or lightning's crashing through the air, stuff like that. Here's a look at the electromagnetic spectrum all the way from DC to gamma rays. And of course, in the radio and wireless world, we're really interested in this section over here, up to maybe, I'd say for most hams, up to 440 megahertz or maybe a few gigahertz if you're going a little bit higher in frequency. And so here's a kind of a chart that helps us understand the different frequency bands and where the different kind of measuring instruments will apply. Let's go ahead and expand that out. And, at the top, you've got DC, right, which is 0 hertz. That's going to be batteries, power, DC power, that sort of thing. And then at very low frequency, we have AC power, which is in the US 60 hertz. And then moving on up in frequency, we have audio, and that's going to be typically modulation for us or, some other audio thing going on. And then there's LF, low frequency band, that's 30 to 300 kHz. And I called that experimental. Most ham radio stuff really starts in the medium frequency range, which is 300 to 300K to 3 megahertz. And of course, HF band's extremely popular, and VHF and UHF. So I chart this out because we're going to talk about digital multimeters, and of course, they're really a low frequency measuring device, really good at DC, the AC power, and most of them will do pretty well on audio, depending on the model, but they don't really go much higher in frequency. And then when we get into the RF arena, that's where our SWR meter can be very useful, or maybe an antenna analyzer. So we'll talk about both of those. Then we'll touch on oscilloscopes. Oscilloscopes actually cover the whole frequency range, right? They can do DC all the way up into, well, it depends how much money you have to spend, but up into the multiple gigahertz range. And that's going to be looking at signals mostly in the time domain. We're going to look at voltage versus time. And we can also look at signals in the frequency domain. So here's Here's kind of that time domain view over here on the left. Can you see my cursor?
Yes, we can see your cursor.
Okay, thank you. So, voltage versus time over here. This guy's looking at it versus time, but we can flip it to the frequency domain and look at the different frequency content that's inside the signal. So basically amplitude versus frequency. And so for frequency domain measurements, we can use there's two major types that we may use. One is the vector network analyzer, or a VNA, or the spectrum analyzer. And those usually, the low end usually covers down to kind of audio range, and then all the way up to maybe multi gigahertz. We'll talk about that in a bit. So let's start with multimeters. These things go by a number of names: voltmeter, VOM, DVM, DMM. I usually call them DMM or multimeters. Most of them are digital these days. And the basic idea is it's a voltmeter, ammeter, and ohmmeter combined into one instrument. And they are just a really useful and affordable device. It's amazing how low cost some of these multimeters are. You do DC and AC measurements. And then, of course, some models have added in a bunch of other features: diode test, continuity, capacitance, etc. You can buy them in a bench format. The more higher performance ones are designed to sit on a bench. I think most of us probably just use the handheld kind of meters. And these days, it's mostly digital meters are being sold. You'll still find some analog meters. And there's just a ton of them out there. Here's just a few photographs of some of them, mostly handheld, all digital except this one in the lower left here. It's an old style analog. And so, quick buying guide. I'm assuming most of you probably have a DMM, some kind of multimeter at this point. In fact, what I've noticed is I'm starting to treat them like I throw a toolkit in the back of the truck, or even in my briefcase or whatnot. I'll stick a multimeter in there now. They're so inexpensive and pretty compact that I have them sprinkled all over the house. In general, I think nowadays you buy a digital meter. The main functions are DC volts, AC volts, resistance, and AC and DC current. Should have a minimum of a 600 volt Cat 2 rating. That's the rating that it's a safety rating for what kind of measurements can be made with that are and still be safe. And I think for ham usage, you're probably looking at a lot of low voltage stuff. Plus, you may want to measure the power line, which is 120 volts AC, or maybe you need to measure 240 volts AC. But we don't in a house residential environment. We usually don't go much higher than that. Other features to consider: continuity test, little beeper thing, beeper mode, diode test, auto range. Actually, the more I was looking at what the latest low cost multimeters are available, and a lot of them have auto range now, which is just really nice. You just click it on auto range and it figures out what range you need to be on. You don't have to go clicking back and forth with the control. So that's very affordable. Just get an auto range. Some people will say, I don't like the digital meters because my good old analog meter has that needle going back and forth, and it can give me trend information. Is the voltage going up or going down? Well, some of the digital ones do have like a bar graph in addition to the digital readout, and that's pretty handy. Battery test mode, and again, true RMS is getting very affordable. That I'm not going to go very deep into that, but it's for waveforms that are, all meters will handle waveforms that are sine waves. If your waveform is not a true sine wave, then a true RMS meter will do a better job of more accurate job of measuring that. So go out and buy a DMM, maybe buy several. Buy them as a 6-pack. Here's a classic one. I actually just purchased one of these on eBay just because I wanted to have it. And then I did a little bit of research on it. It was actually introduced in the 1930s by the Simpson Electric Company, but they're still, and of course the design has changed a bit over time, but the same basic meter is still sold today, which is pretty amazing. It's like 90 years. And then a lot of times I go into Amazon. It's almost like a hobby for me now. It's like, what is the lowest cost, credible multimeter from Amazon these days? And this one popped up, and it's got all the key features. It's auto ranging. It's TRMS, means true RMS. It gives you a pretty nice set of test leads, and sometimes you can't even buy test leads for $17, and they're giving you the whole thing. Don't know anything about this brand. I don't even know how to say it. The Cinda or something like that. And so I have not used this. I don't know if it's a good meter, but usually, well, you go look at the reviews, right? They got 4.5 stars there. So I'm pretty sure for $17, that's a pretty darn good value. Then this one, I do have several of these. It used to be the low-cost meter I liked on Amazon. It used to be about $20, and I don't know, inflation, it's all the way up to 28 now. But it's pretty representative of these low-cost meters. 3.5 digits, which is enough for your normal hobby kind of use. Typically, they're about, the accuracy is about 1%, which is also going to be good enough. It has diode test, continuity test. It's an auto range. It's got this little battery feature on here where you can do a battery test, and what that does is puts a little bit of a load on the battery so that it verifies it can maintain its voltage while you're drawing some current out of it. And then it is Cat 2 rated. And then here's the inside of this thing, because you go, how do they make these things so inexpensive? And the key thing is there are available these DMM ICs. This one is underneath this glop substance to sort of hide it, I guess. And it does almost all the voltmeter or the multimeter functions. Then you see it's got a bunch of resistors and capacitors, SMT sprinkled around, and this is a quad op amp. I'm not sure exactly what it's doing. Some signal processing, probably some kind of function. It's got a little beeper for the continuity test, and then has protection fuse. So if you overload the thing, it'll try and protect itself. Runs off of two AA batteries. So there's just not a lot of circuitry here. And so they can make them pretty inexpensive. Another meter I have is this clamp meter. And, normally when you make a current measurement, you of course put this thing into current mode, but you use the proper inputs here for the current measurement. But the key idea is the current will actually flow through the meter to make a current measurement, and that means the meter is going to try and be a short circuit. So 0 ohms, and just let whatever current's going to flow based on the measurement. So that means you need to be really careful when you put it into current mode. Don't hook that up to a high voltage source. You might get a lot of current flow, and that fuse is going to blow inside. So that's one way to that's the most common way to make a measurement for current. But they also have these current clamps, which is pretty cool. And this thing opens up, and you can clamp that around the wire that you're trying to measure. And basically this clamp acts like a transformer with the wire. And this particular one is only measures AC current that way because of that, how that clamp works. Which for $28, that's pretty good. It's also got your other two connectors down here, so you can do your other DMM measurements. And then there are clamp meters that will also measure DC current. They're a bit more expensive. They're also coming down in price, but and that would be, you know, if you're doing any kind of automotive stuff or DC current measurements, that might be the way to go. Yeah, I should say something about safety because, you know, a lot of ham radio stuff, we don't have to worry too much. But if if you're measuring 120 volts AC, like this measurement here, you know, the probes really help you. They're insulated and all that. So if you're careful, you'll be fine. But if you get your fingers onto the metal parts of those probes, you are going to get one heck of a shock because 120 volts plus lots of current available, you know, 15 or 20 amp kind of circuit can really zap you quite well. I can't see you guys right now, otherwise I'd ask for a show of hands of who's ever been zapped by 120 volts. Then the other place that we encounter is 12 volts DC, which by itself 12 volts is not that dangerous, right? You can put your finger on a 12 volt power supply and it's not going to hurt you. But like a car battery, as a good example, or any of these high capacity batteries can put out a lot of current. And you know, if you've been around auto mechanics, you can usually hear the story about how the guy dropped the wrench across the battery and shorted out the positive and negative terminals, or shorted the positive to the ground on the car or something like that. And man, lots of current flows, and the big danger is the battery may explode. So be careful both these situations. So that's multimeters. I can't see the chat, but if you want to ask any questions, you could pop something in there, or you could just holler on audio. We don't have that many people in the meeting. Otherwise, I'll move on to measuring SWR.
Nothing yet.
Okay, thanks. Oops. Okay, as I'm sure all of you know, standing wave ratio, SWR stands for standing wave ratio. Sometimes it's called voltage standing wave ratio, so it's VSWR, and then people will say VSWR as a shorthand. And basically it's measuring the match between a source, which for us is usually a transmitter, and a load, which is usually the antenna. Perfect match, of course, is SWR equals 1, or sometimes we'll also say 1-to-1. SWR is always greater than or equal to 1, and anything greater than 1 is less than, something fell off my slide, less than a perfect match, is less than perfect, okay. So here's another look at that. And so if we think about what's going on the transmission line, so we get this transceiver connected up to a transmission line connected to an antenna, and you'll have a forward voltage coming from that transceiver. Unless the antenna is perfectly matched, and for most ham radio stuff, we're talking about 50 ohm systems, or there are some exceptions, but usually talking 50 ohms. And so if it's not perfectly matched, there will be a reflected voltage coming back. And so the way we figure out the SWR is we want to know is where the name comes from, the maximum voltage on the line divided by the minimum voltage. And turns out that's forward voltage plus reflected voltage divided by forward minus reflected voltage. So here's a picture of that. And you can see I don't have if SWR was 1, then this would be flat, and here's an example of the middle one here is pretty flat. There's not a big variation of the standing wave, and then the other two are a lot more extreme. And so that's actually what's going on the transmission line, and that's where the name comes from. In many ways, I wish we haven't adopted the SWR nomenclature, because the way I actually like to think about it is it's all about impedance match. It's that when I look into this transmission line from the transmitter end up into the antenna, ideally I want to see 50 ohms. And if I see 50 ohms looking in there with some kind of measuring device or whatnot, then the SWR is 1-to-1, and that's what we want. And there's other ways to describe that, so that the impedance Z equals R plus JX. The impedance may be complex, may be real if it has no capacitance or inductance, and it's just a resistive value. And it's actually pretty easy to compute SWR from the impedance. You just take the load divided by Z0. Z0 is 50 ohms for us, or Z0 divided by the load impedance, whichever one gives you a number that's greater than 1. So, for example, if we had, what's the SWR when Z sub L is 100 ohms? Well, it's either 100 divided by 50 or 50 divided by 100. 100 divided by 50 gives us 2, so that'd be an SWR of 2. There's a couple other ways to refer to all this. We could refer to the reflection coefficient, or we could refer to the return loss, where return loss is just that reflection coefficient expressed in decibels. And for like electrical engineering, you tend to use return loss. It's a little bit more commonly used, although we'll still use SWR. So again, perfect match is 1. Anything greater than 1 is less than perfect. We may show it as 1:1 or 2:1 or even just 1:1. And then in general, an SWR of less than 2 is a pretty good match. Greater than 3 is considered a poor match, and then SWR greater than 5 is a very poor match. And I will say, there are applications where we don't worry so much about SWR. Like a common one is if I use open ladder line to drive a dipole or a doublet antenna, the SWR might be pretty high on that ladder line, so I'll have to use an antenna tuner. But the loss is pretty low, and we don't care so much about the actual impedance match on the line in that case. So there are exceptions to this, but usually, most cases, we're looking for a good 50 ohm match. And then, SWR, I think I will skip this. This is just a little bit more about reflection coefficient and return loss. So let's get back to the meter. So an SWR meter is sometimes called a reflectometer because it's measuring that forward voltage and reflected voltage. And it needs to be inserted in line with your transceiver, SWR meter, and an antenna. So you probably have like a little jumper cable here to connect between transceiver and SWR meter. And then, of course, most of the full-featured HF transceivers these days have an SWR meter built into it, which is pretty handy. When I have an IC 7610, and when I'm operating that, I always have the SWR meter visible to me, just kind of as a comforting factor that something weird didn't happen out on my transmission line or antenna. Cool. And so basically the SWR meter is going to have some kind of directional coupler or bridge inside it. It's going to pull out the reflected voltage and the forward voltage. Is going to be an SWR calculation, and we show that somehow on a meter, some kind of display. So here's a really nice one that I have. It's the Diamond SX200. It's actually SWR and power meter. You select that down here. And the frequency range is 1.8 to 200 megahertz. So that's going to cover your HF bands up into 2 meters, which is pretty good. Different power ranges on the power meter, and it costs about $100. Then there's, like many of these SWR meters, there's a cal function there. You flip the switch. Okay, you push transmit to get some power into the system. You hit the push to talk button, and so you got power flowing through the meter to the antenna. You flip this to cal, and you adjust this knob until the meter reads the full scale where it says cal, and then you flip this switch back to SWR, and now the meter will start to read the actual SWR. And that's just the method that this style of meter handles the calculation of forward voltage and reflected voltage. Uses that cal system. That's pretty common. Here's one that has a cross needle meter. So there's actually 2 meters built into this thing. One of them is reading the forward voltage, one's reading the reflected, and where the 2 needles cross, you'll read out the SWR that way. And then this thing is quite popular with some of the more advanced stations. This is an external meter that it reads SWR all the time, and it's got a remote coupler, so you can position this thing wherever you want. You can put it really close to your antenna. Okay, that was SWR meters. Here's antenna analyzers. So the big difference with the antenna analyzer is it has its own little transmitter built in. It puts a signal out, and then it will read the SWR or impedance or whatnot based on that. So we don't use our transceiver or transmitter in this case. We just take the antenna analyzer and hook it up to our transmission line and see what the answer is. This MFJ 259 is real popular. It of course is getting a little bit old here, and I don't know that MFJ even makes it anymore. But you see what's going on here. It's got a digital readout and a couple of analog meters. It covered HF up through 170 megahertz, and they've got a couple other versions. And it'll measure SWR, it'll measure return loss, impedance, reactance, resistance, all that stuff. And it'll give you impedance with in terms of magnitude and phase as well. So it's got quite a capability. Here's a close-up of the actual measurement. I've got it here. It's set to 143.94 megahertz, and the SWR is 1.5, and it reads out the actual resistance and reactance. Let's see, these things. Couple of usage tips. I think this applies for pretty much any antenna analyzer. They're really designed for 50 ohm systems, so you're going to get your most accurate results when you're close to 50 ohms. And or better put, they're not very good at measuring 100 K ohms, right? They're not built with that in mind. Don't use in a high RF environment. You can mess up the measurement if you have a bunch of RF coming into the analyzer. The input circuitry is sensitive, so don't Don't fry the input. Discharge antennas before connecting. Don't apply external voltages like a DC voltage. And don't overinterpret the results. All the analyzer is really doing is looking at the impedance match to whatever you hooked up there. And of course, we like to say if I have a good SWR, then my antenna must be working properly. Well, you really don't know that. It doesn't really tell you if the antenna is radiating well, right? It's just telling you whether it looks 50 ohms. And a great example is dummy load up. I'm going to have a good 50 ohms. I'm going to have an SWR of 1, but those things don't radiate very well. So, but it is usually our best way of getting confidence that our antennas are working, right? Okay, SWR looks good. That means I'm connected up. Somebody didn't run over my coax line with a ditch digger or whatever. Here's another one. I have this Comet analyzer. It's pretty simple. That's one of the advantages of it is just dial in the frequency and look at the results. Goes a little higher in frequency because that catches the 70 centimeter band, and it's a little more expensive, $430. And then here's a more modern one. Rig Expert has a bunch of really nice analyzers. This one goes to 230 megahertz, and it gives you a little graphical display there, so you can see what's going on with your antenna versus frequency, and that can really help with understanding how to tune your antenna or whatnot. There's a time domain reflectometer mode that can help you locate a fault in the system. So if you had a short in your coax or something like that, that feature could tell you how far down the coax line that is. A lot of antenna analyzers have that kind of feature. A little more expensive, $550. And then this one is a little newer, and I don't own one of these. I think I might need one. It's pretty compact. It's kind of like the stick form factor. But if you go and do some measurements, you can transfer the data to the PC with software to get a bigger display of the data. It's rechargeable, and it's got a USB-C connector, about $300. I've seen really good reviews on these. And then here's one I do have. It's really, they call it an RF vector impedance analyzer. So it's got one port on it, and it goes. The reason I bought it, it goes all the way up to 2.7 gigahertz. I wanted something that would get up above a gigahertz, and that was $160 on eBay. And you can see it's got a pretty nice display there, and then it can also show you via SWR versus frequency. Okay, let's pause there before we go on to scopes. Okay, what's an oscilloscope? An oscilloscope displays voltage versus time. Gives you a picture of the waveform, and the modern digital ones also will give you a readout of what the values are on that waveform, and they're really a good general purpose piece of equipment used by engineers and technicians for all kinds of things. Lots of names for them. Sometimes just call them a scope, maybe a DSO, digital storage scope, digitizing scope. There's still analog scopes. I guess I don't think there's any analog scopes in production, but there's plenty of used ones out there, and they're certainly usable. Sometimes people will call those cathode ray oscilloscopes, and they'll even call them Crow. It's like I remember talking to one customer one day, and he was saying, "Yeah, I got that old Crow over here," and I thought, "What the heck is he talking about?" He's talking about a cathode ray oscilloscope, oscope, and there's a variation called a mixed signal oscilloscope that has some logic analyzer channels included. So here's kind of a typical picture of a scope. You've got, usually 2 or 4 channels. Got nice knobs there for vertical scaling and position, and horizontal knobs, all that kind of stuff. Pretty standard. And then of course you've got here's your display, the voltage versus time. You can just look at it, and if you look at the here it says 1 volt per division, so each one of those divisions is going to be a volt. And same thing with horizontal, 1 microsecond per division, help you interpret the display. Or most of the digital ones will give you a readout of what's going on, give you a peak-to-peak voltage and period of the waveform, and they'll go ahead and calculate the frequency, all that kind of stuff. Skip over that one. There is one aspect of the scope that maybe isn't obvious the first time you use one. The scope does have a triggering function, because in the upper left, if we don't have the trigger operating properly, what we'll get, like here we're just looking at a single sine wave, but we'll get a random collection of sine waves. And if this were live, it would just be, those sine waves would be just wandering all over the display. There's nothing that stabilizes the sine waves, so it's untriggered. Well, so we have a feature called the slope trigger here, where you can hear this horizontal line is saying we're going to trigger when the signal crosses 0 volts, and so that stabilizes the waveform. Or here's another example where the trigger point is moved a little higher. And let's see, on this one it was rising edge. Here we've selected a falling edge, so we're catching the waveform when it's going down. This is really important, otherwise you can't really make a signal, can't view the signal very well. And there's tons of triggering features now that like you can do pulse width triggering and rise time triggering, all kinds of things you can trigger on different parameters of the waveform. Very, very flexible. Key spec on the oscilloscope is its bandwidth. All oscilloscopes start out very flat down at low frequency down to DC, and then the frequency response rolls off, and when it rolls off to 3 dB, minus 3 dB, then we call that the bandwidth of the scope. And oscilloscopes will have a nice slow roll off. We don't want like a brick wall, very steep filter, because that'll create all kinds of ringing in the time domain. So that's your typical response. And so why do you care about bandwidth? Well, here's an example of this is a 100 megahertz digital clock, and if I measure that with just a 100 megahertz scope, I'm actually going to see a sine wave. I'm not going to see the square wave. If I have more bandwidth, here's the same signal with 500 megahertz scope, 500 megahertz bandwidth scope, then I'll see more of the square wave, because I'm picking up more of the harmonics that way. So, probably for hobby use, 100 megahertz is pretty good. If you've got, if your budget will allow it, you might want to spend more than that. Let's see, here's the oscilloscope inputs. They're almost always B and C inputs in the category we're looking at. They usually have a 1 mega ohm input with some capacitance in parallel, and they'll handle up to like 300 volts RMS. So that's a peak voltage is much higher than that. If you want it to be 50 ohms, some scopes will have a 50 ohm input built in, but usually on the lower cost ones, you'd have to add like a 50 ohm load, a feed through termination like this one. What do we actually use these for? We can certainly measure audio signals. We can measure DC as well. We can measure digital signals. Like take a look at what's your Raspberry Pi doing? What are your serial ports doing? I2C, SPI, all that kind of stuff. And we can actually monitor transmitted RF if we want, assuming the scope bandwidth is high enough. You have to be careful. You need a connection method typically you'll want to like monitor your signal on the air. Used to be people bought these things. It was an actual scope designed to to tap into your transmission line and give you a picture of what your signal's doing. Now, it used to be for ham radio, I actually didn't talk about scopes very much because they were just too expensive. Thousands of dollars, or okay, maybe you can find a used one that's more affordable. But as technology's improved, these things have really come down in price. Now, I will confess, my background is with Keysight and HP and all that, so I'm highly biased towards you buy from one of the, let's see, what would we call them? These are from like the top tier companies, Keysight and Tektronix. Brody and Schwartz has some good scopes as well, and they're starting around $600 or $500 for a basic scope. And then you do have the lower cost Chinese stuff. A lot of people like the Regals, more like $329 for even better performance, 100 megahertz scope. Siglent, and I've seen good reviews of that one and the Handtech, and that's pretty amazing at $259 for a 2-channel 100 megahertz scope. So these things are in the ballpark for hobbyist use without breaking the bank. And then these, of course, over time they've gotten more and more features. You got to look at the bandwidth, number of channels, memory depth. Some of them have waveform generators built in. Mentioned the logic channels earlier. A lot of them have a protocol decode. You can decode a serial signal. It'll tell you what the digital value is. FFT, fast Fourier transforms, pretty common as well. All kinds of stuff to look at. Here's a really tiny, low-cost bit scope bandwidth, 20 megahertz bandwidth scope. Pretty darn capable for $145. And does a lot. Has analog, digital channels, all kinds of capability there. And then analog scopes are still around, and they're pretty inexpensive to pick up at a swap fest, and they're just fine. They can make some great measurements. Some people prefer them because of the display is so responsive, and you can see finer detail than on a digital scope sometimes. But you're going to miss those more modern digital features. So there's a little bit of a trade-off. Okay. All right, so that's oscilloscopes. Moving on to vector network measurements, vector network analyzers. So again, now we're definitely into the starting at audio and going up through UHF kind of signals. So these are not going to do you any good at DC. They just don't work that low in frequency or at DC. And this is what you used to have. You used to have like a big box, and it probably costs you $20,000 brand new. And okay, maybe you're savvy, buy one on the used market for a lot less, but they were pretty darn expensive. And here's kind of the typical use: 2-port measurement. It's got the cable coming over to, this is probably a filter of some sort. Yeah, I think it's a bandpass filter if you look on the display, and then and so you put a signal into one end and you measure the signal coming out the other end. And so you can see what's going on there in your circuit. Well, and then this thing came along. The Nano VNA is a very low cost network analyzer. There, last time I looked, it was $59 for the basic version from Amazon. Pretty amazing for what they do. Okay, if I stand it up next to a modern vector network analyzer from Keysight, okay, it's not going to be that good. Okay, we're talking $59 versus maybe 20 or 30,000. So that's fair. Here's some of the specs on that. goes to 10 kilohertz to 1.5 gigahertz. So the frequency range is pretty impressive. You'll see that the measurement range sort of falls off as you go higher in frequency, but these things are pretty darn impressive. Here's one. Well, this one has a pretty small display. This one's a little bit bigger, has a larger display, and it's got N connectors instead of the SMAs there. And actually, there are a ton of variations that have come out on this thing. So like here's one with quite a bit bigger display. So you probably need to shop carefully if you pick up one of these things. And the displays tend to be pretty small, but they do have companion software that allows you to pull the data out and look at it as shown here, which is a pretty nice compromise, right? So now you have this small pocket-sized piece of measuring gear, but you can also connect it to your computer and get a bigger display. This one in particular I found to be pretty interesting because they really worked on the software and made it a little more application specific for ham radio use. So in fact, they have a mode in here that you can just do a single frequency measurement very simply. It basically becomes a simple antenna analyzer instead of a real vector network analyzer. So this one looks pretty interesting to me, but it is a bit more pricier. It's about $200. There's another look at that. So yeah, I should probably back up a little bit. So when you jump to a VNA, you inherently get into the world of S parameters. And so here's kind of the definition of S parameters. We say, well, we have a two-port network, an input and an output. We'll call those port 1 and port 2. Over on port 1, we've got that same, here it's called VI, so it's the same forward voltage or incident voltage that we had when we were talking about SWR. It's the same concept. And then there's a reflection back from that port, VR1. And we've got the same thing going on the other, on port number 2. We've got an input and a reflected voltage. And so the definition of the S parameters is like this. There's S11, S12, S21, and S22. Let's not worry about that too much. S11 is just the reflection measurement over on port 1, and then the transmission measurement is going through the device. It's what it measures the action at port 2 due to what's happening on port 1. So that's called the forward transmission coefficient. Yeah, and that's what the nano VNA does. It'll measure your reflection on the input port, and then it can simultaneously measure the transmission. A full featured network analyzer can actually do the same, can do those two measurements over on port 2 simultaneously, but the nano VNA can't quite do it. That's fine for the kinds of stuff ham radio folks are doing. So if you hook that up, nano VNA has two channels, channel 0, channel 1. Like if you hook up a two-port network, so that might be a bandpass filter, let's say, you'll do the S11 reflection over here measurement, and then the S21 measurement is the transmission through that network. But if I had just an antenna, I don't have a two-port measurement. If I just have an antenna, I'm just going to make an S11 reflection measurement over here on channel 0, and I'm not going to hook this port up. So here's how it's labeled on the nano VNA. You've got channel 0 shows you that's the S11 measurement, and then channel 1 will be the S21 measurement. And you will usually get a calibration kit that consists of an open, short, and a load. And you actually need to do a little calibration process before you use that. So that's perhaps a disadvantage of a nano VNA compared to like an antenna analyzer. Antenna analyzer, you pretty much turn it on and and go. Here you've got a little bit of calibration process to go through, and frankly, a nano VNA is pretty darn complicated. I know a lot of people that have used them and just get frustrated because there's so much going on in there. But if you're kind of a techie and you like that kind of stuff, you'll probably do just fine. So when we do the calibration on the reflection measurement, we'll put that open, short, and load on, and the analyzer walks you through that. And then for the transmission measurement, you do one measurement with it just disconnected, open, and then you put a through connection on there. Okay, so here's some example real-life measurements. This is a 2-meter Yagi from M². It's a 9-element Yagi. And so here we're measuring SWR and return loss versus frequency. So you can see that, let's see, the bottom one is SWR and the scale's over here on the right. So you can see kind of in the ham band, let's say 144 to, actually it's the low part of the ham band, 144 to 146, we've got a pretty good SWR, less than, what is that? That's about 1.4, I think. And then out away from the ham band, then the SWR tends to increase. And then so here's the actual impedance of that antenna. It's the magnitude. So you can see kind of in the center here, we're pretty close to 50 ohms. And then as we get to the outside the ham band, then I shouldn't say outside the ham, out of the design area, like up around 146 megahertz, then the SWR starts to, or the impedance starts to go up, gets up to about 100 ohms right there. And then we can measure R and X, the resistance and the reactance of the antenna. Same thing, is pretty good in the center band, and then it drifts off outside of that. Here is a bandpass filter. So here's a transmission measurement, and this is set up for being a bandpass right on the 2-meter ham band. So 144 megahertz is about there, and 148 is about there. And it's nice and flat in the center and rolls off quite well. It's a meter from DCI, really nice for preventing interference. That's the same filter with measurement zoomed out a bit. Okay, last but not least, spectrum analyzers. Yeah, so again, we're frequency domain in the down to audio, all the way up into the high RF range. And just like the VNA, the nano VNA, there's this thing called the tiny SA spectrum analyzer. It looks very similar. This one has 2 inputs. There's a input that goes all the way to, starts at 0.1 megahertz up to 350 megahertz. So that's going to cover most of your ham radio operation. And then there's a high input, this other SMA, and that'll go all the way up to 960. Dynamic range is pretty good. Display is pretty small, cost $70. There again, a few years ago, if you wanted to get a spectrum analyzer, you're probably looking at thousands and thousands of dollars, and maybe you go look for a used one, but it was out of reach for a lot of people. This is quite affordable. Yeah, this is a harmonic distortion measurement right here. So here's the carrier, the frequency, and then you see the harmonics at integer multiples. Not very good harmonics. They're only about 10 dB down. Must be a low-cost transceiver. And then again, you can get a software app to pull that data out and look at it on a PC. So that's good. And yeah, you can look at your harmonic distortion. You can also look at spurious emissions in general. And then here's our friends from Regal again. This spectrum analyzer is about $1,000 and I think has pretty reasonable performance. So that's within the range of a hobby kind of instrument, and I know a lot of guys have purchased these and been happy with them. Or you've got the used equipment market. I've got one of these. It's an old HP 8950. It's kind of a workhorse that's been around forever. I think I paid less than $500 for it, and it's just a good old piece of equipment that works just fine. And that gets us through spectrum analyzers and the end of my presentation. So thanks for listening.